For the last few weeks, we've been talking about spontaneous electrochemical reactions, where electron flow is driven by a negative delta G of the reaction. We're now going to shift gears and talk about electrolysis. And electrolysis is a process where the chemical reaction is forced to occur by an imposed voltage. So we're going to force this reaction to essentially run uphill. So if we consider two reactions, the reduction of copper and the oxidation of water to form oxygen and protons, we can calculate the cell potential for this reaction, and it's negative 0.893. So to drive this reaction in a non-spontaneous direction, we would have to apply about 0.9 volts positive to allow this reaction to occur. And we can do that in a simple electrochemical cell, but we would replace the simple voltage measurement with a variable battery, a power supply. So that's where we're going to get the energy. The cell isn't going to provide the energy. A battery or a power supply is going to provide the energy to drive these reactions in the non-spontaneous direction. We're also going to measure the current that flows through this circuit when we drive this reaction with an external voltage. So the reason we are going to do this is that if we measure current as a function of time, we're essentially measuring the total charge. Q is equal to current times time. And if we divide by the Faraday constant, we can calculate the moles of reactants. So in the previous example, we can figure out how much H plus is produced or how much copper 2 plus is consumed. And this is useful because we can now do reactions, acid-base reactions, for example, that would require H plus, or metal ligand reactions that could involve copper. So this electrochemical cell becomes an electrochemical reagent dispenser, and that's what we're going to talk about today. The problem is that the cell potential, that 0.9 volts, isn't quite right. So we have E cathode minus E anode, but we have to add three additional terms. OP stands for overpotential, IR stands for resistive potential, and CP stands for concentration polarization. These terms are due to the fact that we're actually passing a real number of electrons through the cell. So let's begin with overpotential. It's the voltage required to overcome the activation energy of an electrode reaction. So let's take a look at a diagram to get a sense of how this would work. If you think of electron transfer as a kinetics process, we can remember that kinetics have the reactants and then an activation barrier and the products. And the rate of the reaction is related to this activation barrier. Now, in most reactions, we heat things up to increase the kinetic energy of the reactants to drive the reactants to products. Drive the reactants to products. But in an electrochemical cell, we can increase the electrode potential to essentially do the same thing. And it turns out that this overpotential is due to a number of factors, but the two biggest ones are the chemistry of the electrode and the species that's being oxidized or reduced. So that makes sense. If you're doing kinetics, the composition of the products and reactants matter. The electrode is one reactant, the composition of the reactants matter. The electrode's one reactant, and in this case, hydrogen or oxygen or others. And this table actually gives you an idea of the magnitude of those overpotentials. They can be up to a volt. Sometimes we use these to prevent reactions to occur, and in other cases we use platinized platinum to actually enhance the rate of the reaction. Notice the overpotential on platinized platinum is quite low for hydrogen. So if we want to create a fuel cell, for example, we often use hydrogen electrodes to decrease overpotentials. That's the first term. The second term is the ohmic potential, and it is due to resistance in the cell. So if you're passing a lot of current, the voltage drop across a resistor equals V equals IR. So we actually have another voltage we have to overcome, and it is the ohmic potential. And it is related to the resistance of the cell. Now, depending on how we're setting it up, we can add a lot of salt, an inert electrolyte, to the cell, and we often do that to decrease the resistance. If we decrease the resistance, the ohmic potential can be small. And finally, we have one more term called concentration polarization. And concentration polarization is due to the fact that when you transfer electrons, you change the concentration of species at the cathode and the anode. So if we change the concentration at the cathode and the anode, the bulk concentration is different than the surface or the electrode concentration. So let's think about what would happen if this is your electrode and you are reducing the species, whatever this is, let's say that's copper 2+, and you're reducing it onto the electrode to make copper metal, then as you increase the current, the copper 2+ that's out here will decrease because you're reducing it onto the electrode, and this decrease in concentration, as a result, changes the concentration right at the surface of the electrode, and if the concentration at the surface of the electrode changes, then the value of the voltage changes as defined by the Nernst equation, where P is products and R is reactants. So this can occur at both electrodes. You can have concentration polarization, where you're decreasing the species that's being reduced and you're increasing the species that's being produced, it's being oxidized, and they both tend to drive the required voltage to higher values. We often stir the solution to decrease the magnitude of concentration polarization. Well, the bottom line is that when you add these together, the overpotential, the ohmic potential, and the concentration polarization, they all oppose the desired reaction, and because of that, we have to apply a higher voltage. Now, this is a bit of a problem, because what we're really interested in doing is tuning the surface of the electrode to do a specific reaction. And we got these terms which are related to current, and we're interested in measuring current as a function of voltage, and we sort of put ourselves in a chemical box. We want to measure current independent of voltage, but the two are intimately tied together because overpotential, ohmic potential, and concentration polarization are current-dependent phenomenon. All right, so this simple positive 0.893 that would be required almost is never true. So to get around this, we don't use a conventional 2-electrode cell. Instead, we're going to use a 3-electrode cell. This is a clever invention, and in fact, the Nobel Prize in Chemistry was awarded to the scientists that figured out how to do this. And what we're going to do is we're going to divide the cell up into essentially 2 circuits. So let's take a picture to see how that works. We're going to have 3 electrodes. We're going to have an auxiliary electrode. So let's call that the anode. We're going to have a working electrode, which we will call the cathode. And then we're going to put in a reference electrode. Now remember, reference electrodes don't like to have a lot of current going through them because then they're no longer at a constant reference potential. So the way we keep current from going through here is we put a high impedance potentiometer into the circuit. So between this electrode and the reference electrode, we can measure a potential. If this potentiostat or potentiometer has a very high resistance, no current will flow. And if no current flows, I don't have any ohmic potential, and I don't have any concentration polarization, and I don't have any overpotential for this circuit. And then what I do is I electronically communicate this voltage to the potentiostat. Now the potentiostat is a battery which will drive the potential of this electrode to meet whatever value the potentiostat asks for. And I should put an ammeter in right here. So let's go ahead and do that. Let's put an ammeter in, put an arrow, put in a big, whoops, sorry. Put in a pen. We'll put in a big A right there. That's really ugly. We're going to put an ammeter in there. And so now that ammeter, so this potentiostat is going to feed back into there. This voltage is going to feed into the potentiostat. It's going to adjust the potentiostat to get this electrode at the right potential. And then this ammeter is going to measure the current that flows in that circuit. A 3-electrode potentiostat. And we'll come back to this again in the next couple of lectures. Okay, so now armed with a way to make reagents electrochemically, we can do a technique called coulometry. And coulometry measures the number of moles of electrons that participate in chemical reactions. So we're going to produce electrons, and we're going to count them. I'll give you 2 examples of how we can do this. If we reduce water to produce hydrogen, we will also produce hydroxide. So if the cathode is driven to reduce water, we can produce hydroxide and do titrate an acid. Alternatively, an anode, if we were now to oxidize water, we would produce oxygen for protons and electrons. And in that case, we could produce hydrogen ions, so we could titrate a base. So these are electrochemical methods that allow us to produce acids or bases. So we're now mixing together our acid-base chemistry and our electrochemical techniques. And the instrument that I'm most familiar with that does this every day, probably in several places in the ocean, is the CO2 Kilometer. A CO2 Kilometer is a dedicated kilometer designed to measure the total carbon dioxide concentration in the ocean. And it has a bunch of components. This is where the sample bottle goes. That sample tube goes back over here into this pump. And somewhere in this pile of glass, right in here, there's a reaction chamber. We're going to react acid with the seawater samples. And then that gas that's produced, which is CO2, is going to be transferred down here into our coulometer. We're going to have a computer that's going to monitor these reactions. And this device is capable of measuring the total concentration to CO2 much better than 0.1%. So let's dig in a little bit and see how this instrument works. So I have a schematic from a commercial coulometer that will sort of make this easier to see. So we're going to start with a reaction flask. And our reaction flask is where we would place a sample of seawater. So we will take seawater and carefully put a certain volume of our seawater sample in the reaction flask. Then we're going to take an acid dispenser and we're going to stick some strong acid into this reaction flask. So what that does is it takes the carbonate and the bicarbonate that's in the ocean. If you add excess H plus to it, you form carbonic acid. Carbonic acid, again, is hydrated CO2. So this carbonic acid, will produce carbon dioxide gas in this chamber. It's like, putting acid in an antacid. You get CO2 out. You also produce some water, and you produce some sodium ions. All right, so we want to leave the excess acid behind. We want to leave the sodium ions behind. We're going to leave the water behind, but we want to now analyze the CO2. So the way we do this is we recognize that CO2 is a gas, so we can push it out of the cell using a carrier stream of CO2-free gas. Typically you use nitrogen. You pass it through some base to get rid of any residual CO2. That bubbles through my flask. As it bubbles through my flask, it strips out all the CO2 that I produced, and it carries it up over. You can put it through a secondary scrubber if you were worried about sulfur, for example, getting carried along. in the CO2 kilometer, I don't think there's a secondary scrubber, so it then goes directly into the carbon coulometer cell. Now, this cell is very special. It is filled with ethanolamine. The coulometer cell is filled with a partially aqueous medium containing ethanolamine and a colorimetric indicator. Ethanolamine reacts quickly. Ethanolamine is a base. It reacts quickly with CO2 to form an acid species. When the gas stream passes through the solution, CO2 is quantitatively absorbed. CO2 reacts with ethanolamine to form a strong, titratable acid. Okay, so now my CO2 comes out here, goes into my coulometer. It is now transferred into as a strong, essentially organic acid. And we add an indicator to this solution. And so now the indicator has a pH change of around 7, color change around 7. So it goes from, say, blue to clear as you put in the CO2. We're going to use that indicator as an endpoint detection. All right, so let's zoom in on our coulometer. So our coulometer is going to consist of 2 or 3 electrodes. We are going to produce hydroxide at the cathode, and we're going to produce solid silver chloride at the anode. So these electrodes aren't right. I grabbed this diagram from the book. All right, so let's see. In this case, our cathode will produce hydroxide, our anode will produce solid silver chloride, and this blue solution is our CO2 ethanolamine. And now what I've got is a little spectrophotometer, so I'll have a beam of red light, passes through that solution. It detects the intensity of the blue indicator, and over here I'd put a detector. So this figure actually incorporates many components of the systems that we've used in lab. We're doing acid-base titrations. We're reacting hydroxide with ethanolamine. We're producing our reagents electrochemically. We're producing the hydroxide by transferring electrons through the circuit. And we're detecting the endpoint by measuring the change in the absorbance of visible light. And of course, there's an ammeter in here. And since the ammeter measures how many the current over time, we can integrate current over time, divide by NF. That'll give us moles of reactant. So essentially, that'll give us moles of hydroxide. And since CO2 is directly proportional to hydroxide, we can measure CO2. So, principle of the CO2 kilometer is convert any form of total CO2 into carbon dioxide. Transfer the carbon dioxide into a reaction cell. React it with an amine to form a titratable acid, and then titrate that acid using base produced electrochemically. So the advantages of coulometry are precision. Because you can count electrons really carefully, it's very precise, it's sensitive, and you can actually, at times, generate reagents in situ, which means in the reactor, that might not be stable. So if they're not stable, you couldn't put them in, say, a burette. There's essentially 2 ways we could do coulometry. One is constant current. So we will apply a constant current, and then we just measure the time it takes for the reaction to occur. That's a simpler system. And what we typically do is controlled potential coulometry. So we set the potential in the electrode. That allows us to absolute guarantee that we're only producing, say, hydroxide in our case. And then we integrate the current versus time. This method is slower, but much more selective. So in either case, the electrons that are consumed are measured over the course of the reaction. That's it. That gives us an introduction to coulometry. Stay tuned for our lecture on next Tuesday, where we'll talk about voltammetry and the ability to measure current as a function of applied voltage.